Hello, everybody. How's everybody's week going? I guess it's just starting. Everybody looks kind of dead right now. Is this the sort of that time in the semester that everything's just dead? Lots of work going on.
I actually feel like it's more just the midday after lunch.
It's just the time of the day. We're always dead. No. If you didn't notice up front, there's two sets of handouts where they correspond. Whoa, I'm not even sharing my screen up there. Let's do that. Where those notes packets correspond to files is there's a notes2.pdf and a quiz.pdf. The quiz is the answer key for the in-class quiz that we'll have next week sometime. And again, it's just going over the definitions of things that we've either already covered or we'll finish going over those definitions today. The sort of physical-ish format of that is everything in the boxes for all these definitions are things that you will have to, they won't be there on the actual quiz and you'll have to fill them in. So these are all the definition-ish things that like come up over and over and again that you really have to know exactly what the definition is in order to get, say, true and false question correct, or in order to get really any of the questions correct. There's a number of theorems that we've gone over. There's only one theorem though here that you'll need to know the theorem statement for. And for all of these things, you notice that I'm giving you like sort of half the definition of things, like the problem setup. So you don't really need to remember like everything, just the sort of the formulas. The most important bits are the parts in the boxes. This is, yeah, so it's all from these first two chapters in the textbook, and this other set of notes that also passing out today is really just has a bunch of problems that are like, can you apply the definitions in like the most basic possible ways? There's no super interesting sort of problems in this note packet. It's just everything follows immediately from all those definitions. So memorizing those definitions will help with going through all of these problems, and again, your next midterm will have problems very similar to the ones on this note packet. And going through this note packet will also help you memorize those definitions, because it'll help you get a sense of maybe why we care about those definitions or why they are the way that they are. Today, we might get to working some of these problems in class, but most of these problems we definitely won't do it all in class. They're more for you to practice for the midterm. Any questions on anything sort of administrative like that? Or, yes?
Is the next project probably be like next week?
Yeah, so the question is, when exactly is the next project going to happen? I want us to get through the chapter 3 worth of material before we do the next project. So that probably means like, yeah, next week-ish. Good question. Any other questions? Okay. There we go. So yeah, we started going over this first set of notes for chapter 2. We'll do a quick review of all the different terms. Again, one of the, I think the hardest parts of especially this portion of the class for students is that there are a lot of very technical definitions and terms and theorems, and it's hard to like really appreciate the motivation. Why do we care about all of these things at this point? You'll just have to trust me a little bit that in like a week or two, it'll start all tying back in together into really practical things. The very last problem in this set of notes, which we'll hopefully get to today, is going to start getting our feet wet into those practical things. But the main idea of what we've talked about so far is that there was this finite up here. This equation 1 is somehow our generalization bound. When we have this E out is like the thing that we're actually interested in, but we can't measure E out. We can only measure E in. E in is the training error, the error on our data set. E out is the true error, the error on like the universe. If the universe were to supply us an infinite number of new samples, what would our error on those new samples be? And we can't know E out directly, but we can somehow bound it based on E in. It's not going to be too much bigger than E in. And these sorts of bounds are called generalization bounds because the generalization error is the difference between E out and E in. And we talked about that there's these bounds on finite hypothesis classes. If you have a finite hypothesis class, this M right here is the size of that hypothesis class. And so as the class gets bigger and bigger, our generalization error gets also bigger and bigger, but not by too much because it's the log of M right here. And then what we're building up to is that all of the really useful classes that we want to use are all infinite hypothesis classes. So the first example of that useful class was the perceptron class in D dimensions. We talked about that on like that bank example of providing a bank loan. And this type of bound up here, not useful for infinite hypothesis classes because this M is infinite. And so it's a totally meaningless bound. We just get the A out is less than infinity, which sure, that's not helpful. And so we're building up to develop something that looks like this, where our bounds on this thing called the VC dimension. And so we need to figure out how we can compute this VC dimension. And once we have these tools, this machinery in place to compute this VC dimension, then we can start working on problems about like, how do we select appropriate algorithms and hypothesis classes for different types of training data based on the VC dimension, that given certain situations, we'll want either a high VC dimension or a low VC dimension. And once we know how to compute that, we'll know how to select those classes. So at this point, we're building up to something that looks like this, needing to be able to define this VC dimension. Any questions on where we're going, motivation, anything along those lines? This all waking you up from your sleep a little bit about whatever we forgot over the weekend and talked about 5-ish days ago. So the idea is that there's somehow, like, instead of the number of hypotheses, the VC dimension is going to somehow measure the effective number of hypotheses. And we started talking about these dichotomies, which are, this is the weird notation up here, but this is a set. The key thing about this is a set. And so it's going to remove the duplicates somehow. And we saw an example of two different, these finite hypothesis class right here, finite to make it a little bit easier to work with, having different numbers of dichotomies. And then where we ended up last time was on this problem down here, talking about this idea of a growth function and some examples down here related to the actual perceptron hypothesis class. So now working with infinite dimensional things. And in some sense, the infinite dimensional things are less concrete, harder to wrap your head around because they're infinite dimensional. That's just weird. But they're also actually things that you might care about in practice. So in some sense, they might be easier to wrap your head around. And there's a bunch of different key terms up here, this growth function, this shatter, and this breakpoint. We'll be talking about all three of those today. You're going to need to know the definition of all three of those for the quiz and for actually being able to complete all the problems in this class. But the easiest way to understand these definitions is sort of by example. So down here, we're starting with our examples, and then we'll relate those back to these definitions up here. So our beginning example is we're doing the perceptron hypothesis class in 2 dimensions. So that's just so that we can easily visualize things. And we're starting with 3 and 4 as the number of data points. This MH right here, that's the notation for the growth function. Whenever you see MH, that is synonymous with the growth function. And at this point, the important thing about this is that this in right here is the size of our data set. And so we're looking at 3 and 4 data points in our data set. Anytime you see the capital N, that's always somehow going to be the size of a data set. And so looking at these, there's sort of two possibilities about what a data set can look like in 2 dimensions. From the perspective of a perceptron, things can either be collinear, like all on the same line, like this A example up here, or they can be in this sort of triangle shape. And if we have things that are in a straight line like this, we said there's sort of somehow 3 most meaningful hypotheses that we can do where we draw these vertical lines, or they could be like slanted somehow. But the key thing is that we're labeling these dots right here. These dots represent like the X values, the features. We're labeling them with pluses on one side of the line and minuses on the other side. And no matter where you draw these lines, what we talked about is that there's 2 sets of Y values, 2 labels that you cannot get. That there's this plus, plus, minus, plus, and this minus, plus, minus. And no matter like how you were to divide up a line over here, you just can't get this middle thing to be different than the edge things. Somehow the middle always has to be equal to the edge. And so if you were to count up all the possible labelings that can possibly be done on this data set right here, then you get that there's 6 of those possibilities. The dichotomies of a hypothesis class are the total number of different possible labelings that you can get, no matter where you put the lines at. So at this point, there's 6 possibilities for this particular data set right here. The next sort of example where we were left off is this triangle example. And now here, because this middle point is somehow lifted off of this line, it's possible for me to draw a line that separates that, something like this, which would either make that middle one different than these other 2 in some way. And so now it's possible for me to label these all in whatever possible combination of plus and minus that I want. And so since there's 3 points here, 3 points, and 2 possibilities per point, the total number of possible labelings that I can get between these 2 things is 2 to the 3rd, which is 8. And so the total number of dichotomies here is 8 between these 3 points. And then the key thing about this growth function, this MH right here, the thing that this example is actually asking us to calculate, is that it's the maximum of all of the number of dichotomies over all possible data sets that you might consider. And so even though we have one particular data set that has a number of dichotomies is 6, this other data set has a number of dichotomies equal to 8. And so red, the MH of 3 equals to 8 because it's the maximum over the number of dichotomies. This MH of N right here, MH of 3 is the maximum over all possible data sets of the number of dichotomies. That's what this notation here is telling us, that this H applied to the data set is the dichotomies of that data set, the total possible ways that that data set can be labeled. There's 8 of those possibilities. And so MH of 3 equals to 8. Are there any questions about any of that, any of those definitions? I realize that it's been a while since you've seen all the previous definitions, and so it's okay if it's taking a few minutes to remember those, or if you don't remember those previous ones, totally okay to ask clarifying questions about some of those things. Chuck?
range is the maximum possible that you can generate from that number?
Exactly. It's the maximum number of dichotomies on any possible data set of size 3.
Under the learning.
For that particular hypothesis class. Yeah. Yeah, so this is a function of the hypothesis class right here of this H. We're specifically looking at the perceptron hypothesis right now. So we're specifically looking at, we've sort of seen before that you visualize the perceptron by drawing straight lines in 2 dimensions, and one side of the line is a plus and the other side of the line is a negative. And so for a different hypothesis class, this number would be different, but for the perceptron, it's equal to 8. Good question. Any other questions about anything right now? Okay, then one of these, so a fact right here, just something that we're not gonna sort of prove formally, but something that you should be like keeping in the back of your mind, especially for true false-ish sort of questions about these hypothesis classes, is that the number of dichotomies for any particular number is going to be less than or equal to 2 to the n. So why is that the case? That the dichotomies, again, are the possible labelings of the data points. And so every data point can be labeled as either plus or -1. So that's where the 2 comes from, and the n is the number of data points. So if you ever get something that's different than this, that's above 2 to the n, then you know you've done something wrong, that it's going to be less than or equal to 2 to the n. Let's think about this word shatter right here. So this is something we didn't talk about last time. We say that a hypothesis class H can shatter a data set if any of the following equivalent statements is true. So H is capable of generating all possible dichotomies. So on x1 to xn, we know that the maximum number of dichotomies is 2 to the n. So here, this size of the number of dichotomies equals 2 to the n. That's equivalent to saying H is capable of generating all possible dichotomies. And similarly, this is what the actual set of dichotomies looks like. Like it's either a negative or a positive 1 in each location, and there's n of those negative and positive 1s. So all these statements are equivalent to each other. I usually think about this one as being at least for me, the simplest one to think about. Sure. So here, let's remind ourselves like exactly what a particular dichotomy looks like. Up here, the dichotomies look like they're plus or minus 1s, and you have a plus or minus 1 for each one of the data points in your data set. So if we had 4 data points, then there's going to be 4 plus or minus 1s. And so if we had what this notation of the set raised to the n power means is that there's not a whole lot of room here, but I'll draw an example of plus, 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 minus, plus, plus, minus, plus, 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 minus, minus, and so on. For that would be n equals to 4. So whatever the n is it's the size of the tuple right here. And then you have all the possible combinations of pluses and minuses inside of that tuple. And so since there's n combinations of things, and each one has 2 values, that's where the 2 to the n size comes from. So when we say that something shatters a data set, the size is going to be the size of our dichotomies, the number of dichotomies equal to 2 to the n. And so down here, the number of dichotomies is less than 2 to the n. So this implies that it's not shattering the data set. And this implies that it does shatter. Something that's important, a key difference between the idea of shattering and the growth function is that shattering is specific to an individual data set. So on this, we have two different data sets of size 3. One data set does not shatter, one data set does shatter. The growth function, though, is not for a particular data set, it's the maximum over all data sets. And so the fact that we have something down here that's less than this doesn't matter for the growth function. The growth function's the maximum over all data sets. Any questions about the idea of shattering? Sure. So the one key thing to remember about the difference between shattering and the growth function is that shattering applies to a particular data set. That here we had two different example data sets, and one of those data sets is shattered, the other data set is not shattered. And I'm looking at the number of dichotomies here to figure out whether it's shattered or not shattered. The growth function, though, does not apply to a particular data set. It is the maximum over all possible data sets. And so one of the, confusions that students sometimes encounter, especially when you're like talking about things, is that you will use like shattering as applying to multiple data sets, but shattering only applies to a single data set at a time, or you'll talk about the growth function on a single data set. And that doesn't make sense because the growth function is over like the maximum over all possible data sets. So they're sort of related quantities, related things, but different. Question?
So looking like definition 4 then, does that mean that like?
Let's pause that. Question?
How can we tell if it does or does not shatter?
Question is, how do you know if it shatters or doesn't shatter? The easiest way, the thing that I always do to check if something shatters or doesn't shatter is the number of dichotomies equal to 2 to the n. Here, the number of dichotomies is 8. 3 points, 2 to the 3 equals 8, so it does shatter. 2 to the 3 right here is 8. This one, this 6 number is less than 8, so it does not shatter. Another way of thinking about it, sort of relating to this first definition, is that if you can find some combination of pluses and minuses that your hypothesis class can't distinguish. So like here we found 2 different possibilities that there's no possible perceptron that can generate these labelings right here. Then we know that it does not shatter because it does not generate all possible dichotomies. Does not generate these 2 dichotomies. Okay, before we go on to this idea of breakpoint, I want to take a look at this MH of 4 value. And so we'll have a C data set right here that has 4 data points in it. And with these 4 data points, and in particular, no matter what 4 data points you select, there's always going to be some particular point that you can't classify. So if we have, for example, like a plus, minus, minus, plus as the labelings for these data points over here, there's no possible way for us to generate these possible labelings on these data points with the perceptron classifier. And no matter what 4 data points you tried to pick, it would be impossible to generate all possible labelings with them. If you sat down and worked out all possible cases, you'd see that the number of dichotomies here is going to be equal to 14, and the maximum number, so 2 to the 4th equals 16. That's strictly less than 16, and so this number of dichotomies, also the M H of 4, the growth function value. And so this is not shattering. Can't shatter this data set or any other data set. And like the intuition why we care about shattering is that this somehow puts a limit on like how powerful our perceptron hypothesis class is. That we know that if we have 4 data points, then there are certain things that we just cannot do. And that's actually going to be a good thing. We want to have those limits on our hypothesis class because it's going to give us good generalization bounds. So there was the question earlier about now the idea of a breakpoint. So we say if no data set of size k can be shattered by h, then k is said to be a breakpoint for h. So in this particular example, we said that we can't shatter any data set of size 4. So 4 is a breakpoint. So 4 is a breakpoint. And it's also true that if you can't shatter a data set of size 4, you can't shatter one of size 5 or 6 or 7 or anything larger than 4. And so any larger number than 4 would also be a breakpoint. Did that answer your question, Kieran? Any other questions about any of these definitions? Yes. Yes, the question is, can I go over again how I got 14 here? And the answer is that if you try all possible combinations, then you'll see that there's going to be 2 things that you can't label. This one right here and the opposite of negative, plus, plus, minus. All the other possible combinations you can label. So if there's 16 possible combinations, 2 of them they can't, then you'll get 14 possible dichotomies that you can achieve. For another one of the difficulties about this part of the course is there's this kind of question about like how formal maybe do you have to be on reasoning through these things. Doing an actual formal proof that like the number of dichotomies here equals 14 is extremely technical, and nobody really cares about those technicalities. They don't provide any more intuition. Yeah, computing. The most important thing to realize with dichotomies is to be able to recognize, do we shatter or do we not shatter? So is the number of dichotomies equal to 2 to the n, or is it not equal to 2 to the n? Here, after I know these are the 2 possible dichotomies that I can't do, so based on that, I can calculate that the number of dichotomies is 14. But the most important thing here is just to recognize that I can't shatter this data set, and so the number of dichotomies must be less than 16. I'm not sure if that helps answer your question at all. Okay. Check.
So if you like, once you pass a breakpoint, would you say that like that hypothesis is no longer sufficient for working with data sets of that size? Or
yeah, so it's a great question. The question is the hypothesis no longer good for working with data sets that size? We'll see this here in a little bit, but the training error is potentially going to be worse, but the generalization error is going to be better. So in practice, you'll almost always be using a hypothesis with a breakpoint less than like the number of data points that you actually have. We'll formalize that a little bit later. So if you didn't catch that, then that's okay. Your question, Noah? Question is, does shattering apply to elements that have 3 data sets or less? The answer is shattering can, in this case, for this particular hypothesis, the 2-dimensional perceptron hypothesis, we can only shatter data sets of size 3 or less. In general, if you had a d-dimensional hypothesis, then you can shatter data sets of size d. But yeah, so yeah, shattering depends both on your particular hypothesis and your particular data set. Question? Yeah, great question. So the question is like, how does this relate to exactly what I might ask on the midterm? And you definitely need to be able to determine whether something shatters or does not shatter a particular data set. You don't have to prove it, but you'll have to be able to say, just like convince yourself that it's the case, one way or the other.
So if we're often going to be working with like data sets that are larger than the breakpoint for a particular hypothesis, what's the value of like understanding it?
Hold on to that thought. Yeah. Okay, let's move on a little bit. So the main thing here, the main point of this is just to get some intuition for these, like what the definitions actually are saying. And now the rest of the notes are basically going into like the why do we care about these particular definitions. There's a number of sort of like helper theorems in this chapter of the book. This is the most important one right here. And this one is going to capture a lot of the intuition for us about why the VC dimension is potentially a good thing for us to care about. So we'll talk about the intuition of this theorem right here. We're not going to prove any of these theorems, but we'll talk about the intuition of this one. And then we'll be getting into the actual VC dimension heart of the situation. The idea here is, so recall that MHK is our growth function, the maximum number of dichotomies. And we said that MHK, our previous fact, I think it was labeled fact 1, is that MH of K is always less than or equal to 2 to the K. And this is in fact a tight bound. So worst case scenario, we're exponential. What this theorem here is saying, the intuition behind it is that if for whatever reason, we're not at this worst case scenario, we're less than 2 to the K. So if the growth function is less than 2 to the K, for some value of K, then for every value greater than K, we must be polynomial like this. So this here is in particular polynomial. And so we can never somehow be like between a polynomial or an exponential. And if we plot out what our growth functions, like this generic picture of what a growth function looks like, down here will be the K on the x-axis, the y-axis is going to be our growth function. Then it's going to start off going like exponential, growing really, really, really fast until we hit some breakpoint. It's called a breakpoint because we stop being exponential at that point. We hit some breakpoint, and then we go polynomial after that. So down here, this part of the curve is exponential. And then this part of the curve up here, polynomial. And it's a polynomial with a potentially like really high exponent up here. It's n to the k minus 1. This k is our breakpoint. We'll see later on that like these k values can be in the thousands or millions. So it's like a huge polynomial, but the key thing is that it's not going to be exponential. And because it's not exponential, then we're going to be taking the log of this value. And so it'll be log of any polynomial is going to be a really small number. So this is like the key intuition about why we care about these breakpoints, this idea of shattering. Anything over here to the left of the breakpoint, we're shattering all the data sets. To the right, we're not shattering anything. And so the key idea is that once we stop shattering, our growth must be polynomial and it can't be exponential. Okay, so now getting to the VC dimension and start getting into the why do we care? So the definition of the VC dimension right here, the VC dimension is something that applies to a particular hypothesis class, and it's independent of the data set that you're thinking about. So the VC dimension of a hypothesis set H, denoted by DVC of H, or just DVC if it's understood what the hypothesis class is the largest value of n for which MH of n equals 2 to the n. If MH equals 2 to the n for all possible n's, then we say that the VC dimension is infinite. So what our previous statement, that discussion of breakpoints in that previous theorem, implies that for all hypothesis classes after the VC dimension, once our n is greater than the VC dimension, then our growth rate, this growth function, is going to be a polynomial. So this is like the key intuition right here about why we care about the VC dimension and that previous theorem, is that we're going to have a polynomial growth function. When we take the log of that polynomial growth function, so we have the log of MH of n, it's going to be less than or equal to DVC log of n. I'll just say that this is a big O of all of that, because I don't want to deal with that +1 over there. And this is what people actually think about, is that this is equal to O of DVC log n. And so it doesn't really matter, like, I mean, this is potentially a huge polynomial, but because we're taking the log of it, that DVC up there is coming out, and we'll get something linear in the VC dimension. The actual VC dimension theorem that they prove in the textbook has this form right down here. It has the same form as our previous generalization theorems that we've seen for the finite hypothesis class. We've just replaced the M with these M sub H, this kind of like effective number of hypotheses. And that's inside the log over here. So that's why we care about this log up here. If you do the substitution, then this right here is the final, this is the final growth rate that we actually care about. That's the actual generalization error. That people remember. Let's see. So the last few classes with all these different generalization theorems that we've seen, there's been a lot of questions that people have had about, in particular, like, why don't we actually ever plug in numbers for these things? And in this case, the answer is that these numbers over here are not at all close to the best possible numbers. These numbers like this 8 and this 4 right here, this 2 inside of here, not remotely close to the best possible numbers. But what we really care about is that there's somehow this kind of linear relationship between the VC dimension here and the number of data points. That if I double the VC dimension, that I'm going to need somehow double the number of data points to achieve a similar generalization error. The way that I think about it is that, like, if we're thinking about runtimes of algorithms, nobody ever plugs into like the runtimes to actually calculate an algorithm is going to take 37 seconds to run. Instead, we look at these runtime formulas to get a sense of like which algorithms are likely to be slower and faster than other algorithms. And so we'll be looking at this formula here to see which algorithms are likely to have better and worse generalization error. But without actually like plugging in the numbers. In practice, the looseness of this bound, so if you were to like plug in numbers, see how many data points, how big n needs to be for this bound to be meaningful. You need about n equals 10 to the 4th DVC to get meaningful generalization bounds above. For the numbers to be non-trivial, so like less than 1. The error rate's always going to be less than 1. So if you plug in numbers over here and you get something greater than 1, it's sort of not meaningful. But if you plug in numbers over here and get something less than 1, then you're actually at least saying something meaningful. So you need like 10 to the 4 data points for each VC dimension for this to be meaningful. But in practice, you need about n equals 10 DVC. That if you have roughly 10 data points for each VC dimension that you have, then you're going to have pretty low generalization error. And this isn't a hard and fast rule, but it's a rule of thumb that a lot of people use as sort of like a first pass guess on what to do. This bound right here. So I've sort of ignored this log factor. Oh dear. I've ignored that log factor. Turns out that log factor actually is unnecessary. And the best possible VC bound is the best possible is O of dVC minus log delta over n, all in the square root right there. Basically everything without that log n. The book doesn't, or the book's version includes this login because the proof of this is incredibly technical. Even though proof of this login, it's like roughly 20-ish pages inside the chapter of the textbook, plus another 20 pages in the appendix. The proof of this version up here is like twice as long, twice as technical. And when I say this is the best possible, I mean that this bound right here, this applies for all possible data distributions that you might care about. And so there exists some data distribution where this bound, you can't do any better than this bound. On the quiz, you're welcome to write any of these possible equations as the definition for the VC generalization bound, including this one up here. Just as long as you write something equivalent to one of these statements, then you'll be good. This is the one that like I actually remember and use in practice up here, this thing right here. Any questions on any of that so far? Okay. So starting to get a little bit more practical here. We want to compute the VC dimension for the perceptron hypothesis class. And then the next problem will be actually using that to accomplish a real world data mining task. So the VC dimension of the perceptron hypothesis class. We saw before that, so M sub H of 3, if H is 2-dimensional perceptron. So that equals 2 cubed, and MH4 equals or strictly less than 2 to the 4th. And the VC dimension is defined. VC dimension defined to be the largest value of n, where you still get that exponential rate. So the VC dimension here would be equal to 3. In general, if H is d-dimensional, so that's what the problem's actually asking for, then MH of d plus 1 equals 2 to the d plus 1, and MH of d plus 2 equals or is strictly less than 2 to the d plus 2. And so those two facts together imply that the VC dimension equals d plus 1. But again, since people only really, we're not plugging in these numbers into the equations above, we're only thinking about like asymptotic growth rates. Everybody just remembers that it's equal to theta d. And everybody forgets the plus 1, because it doesn't really matter. For very, very sort of trivial fixed dimensional things, my expectation is that you'll be able to figure out what the VC dimension is of the hypothesis class. And that next set of notes has a bunch of practice problems for doing that. But for real world things, then we'll be, I'll basically just be giving you the VC dimension of the real world hypotheses classes, because the proofs of these things actually showing it is super technical and not super insightful. But this is something that VC dimension, theta d, definitely want to remember that, even though it's not something that you're required to remember for the quiz. You won't be able to answer any questions about the perceptron if you don't remember that. Any questions? Okay. So now this problem 3, sort of real world-ish problem, again, going back to our problem of you're a bank and you were using the perceptron to learn a formula for whether or not to issue a loan to a customer. And we're going to use this VC theory that we've developed in this packet and the last few ones to answer some questions about what we might want to do in different situations. So this first situation right here is that we've successfully learned or trained a model on some data set. Key thing here is the number of points, this capital N. But this notation is, again, is going to be the same constant for every problem. And D is the number of features that we have. But unfortunately, we're not getting the good results that we want. And in particular, in this case, the training error of the model is too high. So when I say the training error of the model, again, that corresponds to the E sub n of G, which this is something that you'll have to memorize for the quiz, and you'll just need to know it sort of down pat for all of the questions. Looks something like this: I equals 1 to n, and then this square bracket of h of x sub I not equal to y sub I, like that. And so this value right here is too high. And management has allocated money for us to create a new data set. And we have two choices of things that we can possibly do. We can either use that money to add new features to the existing data set. So this right here, adding new features to the existing data set, that's increasing this D value. Or to add more data points that all have the same features as before. So adding more data points. That's increasing in. And we can use this VC theory. We don't have to plug in any numbers, but using just the trends of this VC theory, we can figure out which one of these two is likely to be a good choice for us. In this case, what our theorem up above states, this VC dimension theorem right here, this big O right there. What that states is that it gives us a bound on the generalization error, that if we increase in, that'll imply that the generalization error, E in minus E out, that will go down. And so that's one of our options, increasing in. Our other option is to increase D. If we increase D, well, that's going to increase the VC dimension, because we said that the VC dimension of a perceptron hypothesis class is equal to D, or it's theta D, so basically equal. So that'll imply that the VC dimension will go up. And if we increase the VC dimension, then our generalization error will also go up. E in minus E out will go up. Whoops, that should be outside that parentheses there. In this case, what the problem is saying is that the training error is really small. So neither of these two things is necessarily particularly helpful for us to make our decision right here. But this is actually the only place, where the number of data points comes into consideration with any of our error terms, our E in, our E out, or the E in minus E out is right here. And so if your training error is small, then increasing the number of data points can't possibly help. Instead, I'm going to make this claim that the hypothesis class H, say the D dimension perceptron, that is a subset of the hypothesis class of the, say, 2D dimensional perceptron, or any dimension where we've increased the number of features, added new features. And up here, when I do this, this E in, we saw before that the training error, if you have a sub-hypothesis class of another hypothesis, we have, so we'll say G sub D contained in that, G sub 2D is contained in that. Then the training error, E sub in, G sub D, must be less than or equal to E sub in of G sub 2D, because at worst, we just pick our original hypothesis that it sort of ignores all the new features. But if any of those features are sort of remotely good features, then our training error is going to actually go down. So that will imply that as D increases, then the training error will decrease. And so based on my knowledge of all these things, I can say that with pretty high certainty that adding more data points is not going to help me improve my training error, but getting new features is the thing to do at this point. And I would go to management and tell them to increase the features that they're using. Jim?
So for the green vector, because there isn't zero decrease, is G2
So the 2D here is
the after
yeah, the intention here is that this is the larger hypothesis set that has twice as many dimensions. You're claiming that this inequality should be switched. Yes. Thank you. I wrote that backwards here. That because this has more possible hypotheses inside of it, then yes, the training error of this side can only go down. Good question. Yes.
So you were saying that using the size of the data set doesn't really hold the training, but it does help the
Exactly. Yeah. So if this question up here, instead of saying the training error of the model is too high, said the generalization error of the model is too high, then I would want to 100% increase the number of data points, because increasing the number of dimensions is only going to make my generalization error worse, but increasing the amount of data is going to make my generalization error better. Yeah. So the question is, why does increasing D decrease the training error? The one way to think about it is think about it like by example, that if my original features are like just super crappy features, like the height and weight of the applicant. Maybe there's some sort of correlation between like height and weight of people and their credit quality, but probably not. And so by getting new features, I can get something that's somehow meaningful to this particular problem, like the examples we had before of the number previous loans or their net worth, or other things that are like more meaningful or add more information than maybe I previously had. And by having that extra information available, that's going to make give me more information to make this this training go down. But the downside is that it's going to make the generalization error go up. Yeah, I guess if there's maybe like just one thing to make sure that you're taking away is that adding more data points can't possibly decrease the training error. The only thing that the number of data points is going to affect is the generalization error. So then part 2 down here is asking about, okay, so we've decided to augment the data set. So now it has 2D features instead of only D features. And now the generalization error is too high. We know that that makes sense, that we've increased the number of features so that that's probably going to help my training error. But the downside is that that's going to hurt my generalization error. And because of this right here, so it makes sense that the generalization error might now be too high. And so according to VC theory, how many more data points will we need in order to achieve the same generalization error that we had before? And we might want to know this to be able to predict it, to go up to management again and say that, hey, we need to spend X amount of money to acquire new data, and you need to be able to predict how much more data should we get. And our generalization error, again, by the VC theorem, the generalization error was the O of the square root DVC. I won't write the log in right here, but their version has the log in minus the log delta divided by n. And so if we double the DVC right here, then we'll basically need to double the number of data points as well in order for this term to stay about the same. So doubling DVC implies need to double n. So our new data set should have 2n data points. If some of the details of this problem here maybe didn't 100% click for you, that's okay at this point. This is the purpose of this problem right here is to give us some like motivation of like these things are going to be connecting back into like real world practical problems here. We're gonna do still need a little bit more technical definitions and things though, in order to like really get into these sorts of problems with more realistic options, larger sets of options that you have to choose from. And so in another week or two, we'll have more complicated versions of this that we'll be working with, and we'll see lots more examples. But the main thing at this point is to make sure that you're comfortable with like the technical definitions and technical manipulations of things. Any questions about this problem? Okay, then for the last bit of class today, we're going to switch over to this other set of notes. And again, the purpose of this set of notes is just to really double down on all these technical definitions and apply them in different situations in order to figure out, get really familiar with them. And this set of notes is going to have like the style of problems that will be on the midterm exam for this like section of material. So there's two problems basically. This first problem up here has a bunch of hypothesis classes, and it's asking you to figure out the VC dimension of those hypothesis classes. You'll be able to check your work on all of these problems because they all sort of come from examples in the textbook. So if you want a more detailed explanation than what we might get to in class today, you can check in the textbook in this section right here. And then this problem 2 down here is all like the proof counterexample stuff, true, false, just like basic immediate consequences of all the various different terms, definitions that we've seen. So let's do problem 1.1. So the set of positive rays in one dimension. I think one of the hardest parts about these problems is just understanding like what do these hypotheses actually look like, understanding this notation right here. And so in this particular hypothesis, it's all on one dimensions. So our x's somehow sit on the number line. And we might have a data set, for example, that looks like this. And what this is saying is that, so if x minus a, where a is some other number on the number line. So say that a, that's the value of a right there. If that x minus a is positive, then we assign a positive value. And if it's negative, we assign a negative value. So in this case, a positive over here and a negative over here. If we want to figure out what are the total, like what are the dichotomies of this particular data set right here, then we would be able to see that we can classify them both. In this case, we can do a positive, negative. That's what we're getting. If we move to the a value, we'll draw the dichotomies in the appropriate colors that match. If we did an a over here somewhere, then that would give us positive, positive. And if we did an A over here, then that would give us negative, negative. And there's no way for us to get a positive negative in this hypothesis class. We can, these are the dichotomies. Can't achieve this labeling. So we have, based on this, that my growth function mh of 2 is equal to 3, which is strictly less than 2 squared, which implies that we're not shattering this particular data set. And this is somehow representative of all 2-point data sets. There is no 2-point data set where I could get a labeling that looks like this with a plus on the left and a negative on the right. And so the VC dimension must be strictly less than 2. If we looked at a single point data set, so pick whatever point you want, single point data set. It's easy to get either dichotomy. It's easy to get a positive label by putting the A value to the left of the X, you get a positive label. If you put the A value to the right of the X, you'll get a negative label. So you get the 2 dichotomies, which is equal to 2 to the 1. So we do shatter this data set. And so the mh of 2 is equal to the 2 to 1. And that implies that the VC dimension must be greater than or equal to 1. And both of those two facts together, that combined with that, those two things together imply that the VC dimension must be equal to 1. Yeah, I probably should have left a little bit more space in here so that I could have written that out maybe more neatly. That's an example of the type of computation that you would want to do or be expected to be able to do for the VC dimensions on a sort of toy but infinite hypothesis class like that. Are there any questions here about why the VC dimension of this hypothesis class is 1? No? The question is here, why did I only consider 2 data points instead of considering, say, like 3 or 4 data points? I know that after, let's see, so another way of saying that the VC dimension is less than 2 right here is saying that 2 is a breakpoint of this hypothesis class. And as soon as I hit the point where I'm no longer exponential, then I know that everything after that point is going to be polynomial. And so if I did consider, say, 3 data points, like those 3 data points, I know that there's no possible way for me to get all of the labelings over here on these 3 data points because I can't get it on 2 data points. So there's no way I can get it on 3 data points. And yeah, so if you're like actually like, I don't know, sitting down and working on these things, you might first guess about, let's try a data set with 3 points and see that you can't shatter that data set. So you go down to one of 2 points, then you'd see you can't shatter that one. And then you go down to 1 and see that you do shatter it. But since I already knew the answer, I just started at 2. Exactly, yeah. If you had gotten 4, then you'd want to keep going up and try it with 3 data points. And so that leads us to this next problem down here with this one. In fact, the idea that this is the set of positive and negative rays in 1 dimension. The only difference between problem 1 and problem 2 is this addition of the sigma out front. Sigmas traditionally, when we're putting them in hypothesis classes, are always just like positive or negatives of things. And so this lets me somehow flip the direction of my my little labeling decision boundary right here. And so with this with this data set, or with this hypothesis class in the same data set as above, it is possible for me to get all the different possible labelings of negative, positive, negative, negative, positive, 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 negative. This last one, this would result in that A value and sigma equals -1. That particular labeling from those particular values up here in the hypothesis class. And so the number dichotomies here equals 4 equals 2 to the 4. And so the VC dimension must be at least 2. But if you were to try it with 3 data points, you can't shatter any data set with 3 data points. And so that implies that the VC dimension here must be less than or strictly less than 3. And so those two facts together would imply that the VC dimension of this hypothesis class equals 2. It makes sort of sense that if we add more like flexibility into our hypothesis class here, then the VC dimension is going to be bigger because we'll be able to, that more flexibility will let us shatter more data points. Any questions about that problem? Let's see, let's jump down to we've got maybe a minute or two left. I just want to highlight that with these problems down here, in the last midterm, I was asking specifically for counter examples for false statements. Since these involve like probabilities for false statements, counter examples maybe not necessary, like easy to describe. So we'll spend a couple minutes on the next class session just taking a look at what a good answer for a true and false versions of these statements would be. But we'll do that next class period, and that will be the end for today. If anybody has any questions about anything at all, then I will happy to answer them after class. Otherwise, I'll see you all on Wednesday.
Thank you.